So for our last unit, I want to talk about just some interesting algorithms. These algorithms are things that you could kind of relate to your day-to-day life, things that would benefit your day-to-day. These are going to be a little bit more advanced than what you're going to need to do for the final assessment. But if you can understand what these algorithms are doing, if you can understand what's going on here, then your final assessment will be a cakewalk. You'll be able to walk right through it. So I've gone ahead and put some comments and added some phrases and stuff, just to get it prepared, ready to go. But let's go ahead and start with our first problem. So let's say you're in your math class and you're asked to solve an algebraic equation, specifically this algebraic equation where you're asked to find x and y. Now, dealing with one variable, super easy. When you add the second variable, there's a few extra steps you need to put in. Well, let's go ahead and just program a brute force algorithm that's going to try every possible number until we find it. So I know that a is 2, b is 3, and n is 24. So I'm going to go ahead and add these. So int a equals 2, int b equals 3, int n equals 24. So now what I need to do is I need to try many separate values of x and y until this equation fits. So let's go ahead and put in this equation in terms of just an if statement. So I'm going to say if x times a, and remember x doesn't exist yet, we'll get to that, plus y times b equals 24. And remember, we're using double equal here because it's the comparison operator, it's not the assignment operator. So this is what we need. So if we're going to have this, we're going to say console.writeLine. We have found solution x equals plus x plus comma y equals plus y. So what this is going to do is if we find a valid solution for x and y, we're going to print it out. However, we need to go back and we need to try some values of x and y. The best way to do that is a nested for loop because we want to try both x and y together. We want to try, y when x is 0. We want to try y, 1 through 10 or whatever. We want to try all these separate values. So let's go ahead and do that. So I'm going to start with a for loop. Let's go for tab. I'm going to press X, enter. You'll see that it renames it. Now I'm going to change this to n. Now, in a lot of these situations and a lot of these algebraic expressions, we would be considering negative numbers as well. Let's just assume that the answer is only ever positive. Adding negative numbers causes weird things to happen when we have to consider more edge cases. But we know that if x starts at 0 and it's this mathematical equation, specifically plus in the center here, we know that if x is greater than n, the problem is already broken. It doesn't matter what the value of a or b is. If it's greater than n, we've already screwed up. So let's do the same thing with y. And then I'm going to take our if statement that we made earlier and put it right inside. So now x equals 0. When x equals 0, we're going to try y equals 0, y equals 1, y equals 2, y equals 3, y equals 4, y equals 5, so on and so forth. This is going to brute force every possible value of x and y from 0 to 24 each, and it's going to test them together. So again, I was saying that when x is 0, it's going to try every value of y. When x is 1, it's going to try every value of y. Therefore, every combination is going to be met. So let's go ahead and run this and see what happens. So I run it and it says we have found solution x equals 0, y equals 8. If we plug this into the equation, we see that it works. We have found another solution, x equals 3, y equals 6. If we plug it into the equation, we can also tell that it works. So it finds every single possibility of x and y that makes this problem satisfied. Now, you may be sitting here in your math class thinking, our teacher gave us 100 of these problems to solve. I'm good at this. I know what I'm doing, but I got to do my homework. I want to get that good grade. I'd rather be playing Fortnite or Apex Legends or whatever you guys do nowadays. In this situation, write an algorithm. The algorithm will solve it for you. So a simple algebraic expression was solved via a simple algorithm. Pretty straightforward, to the point, it gets what you need to do. Now again, if we added negative numbers in here, or if this was subtraction, we'd have to increase the value of n here based on certain parameters, but we're going to ignore that for now. I just wanted to use this as a simple example, solving mathematical problems via programming. So I'm going to go ahead and comment this out, and we're going to move to our next problem. So in your math class, you're also going to run a lot of equations to find the vertical asymptotes. A point where the line never reaches, whatever you're graphing, it'll never reach this point simply because this value equals 0. When you're looking for a asymptote, a vertical asymptote specifically, you need to find the point that makes this value 0. Because when this is 0, it means the equation is infinity. You can't draw, infinity on a graph anywhere. It creates an asymptote. I'm sure you guys are all familiar with that. So let's go ahead and write an algorithm that solves this. Now, your math teachers are all super nice people. They're not going to go through and they're not going to screw you over and give you some insanely complicated problem where a vertical asymptote is going to be at 30,000. They're probably going to limit it between somewhere and let's say -20 and 20, something around there. Let's go up to -25 and 25. So because we want to try for every single value of x that finds a 0 here, in this part of the equation specifically, or this part of the equation specifically, let's go ahead and write a for loop. And we're going to say x enter, and we're going to say from -25 equal to +25. Now I'm saying equal to because I want to check 25. If I just had this here, it would only check up to 24, but I want to check up to 25. Now, in our body of our for loop right here, we need to write the code that checks if x plus 5, given whatever x is at the given time, is equal to 0, we have found a vertical asymptote. So, pretty straightforward. If x plus 5 equals 0, console.writeLine, we have found an asymptote. Did I spell that right? Asymptote. Yes. At plus x. So it's going to say we found an asymptote at whatever x is at the given time. So let's go ahead and run that. So we have found an asymptote at -5. If you look at this equation, by the way, this right here, I was programming this part of the equation in there. But we can see just based on our generic logic that -5 is the only valid option here. It's the only thing that makes this equation equal 0. Specifically because there's no, anything to any power. Once you get to that point, you can have multiple asymptotes. So let's try our next equation, which is a little bit more complicated. So we're going to try this one. So now I can't just put, x root 2. It doesn't know what that is. However, C# comes with this very neat math library. So math.pow, and I'm going to say x, comma 2. What this is saying is it's x to the second power, or x, x to the second power. It's exactly what it is. -3 times x plus 2. Very straightforward. We took this part of the algorithm. If this is 0, we know we have a vertical asymptote. So I'm going to run our code again, and we're going to see we have an asymptote at 1 and we have an asymptote at 2. So very, very easy, straightforward problem. Let's say our teacher was evil and gave us some super hard complex thing. Let's try. We're going to try math.pow x to the 3 plus 3 times this. So instead of doing this, we're going to do x root 3 plus 3x plus x. Yeah, we're going to do that. Let's run it. No asymptotes. If you were to graph this problem on your calculator, you would see that there are no vertical asymptotes in this specific function. So very straightforward, very, very to the point. You plug in your math and you get the right outcome. So the next few problems we're going to look at are really interesting. So you guys may have seen, maybe in your English class, maybe on the internet somewhere, seen these kind of studies that say, humans can read text even if the text is jumbled up or messy or something like that. One of those things that I've seen before is that if we remove all the vowels from the words, just like trying to read a word by itself doesn't really make sense. But if you remove all the vowels from the word, when you go back to actually read a sentence, a human brain can kind of put together the pieces of the puzzle. It can figure out what that saying is supposed to say. So now I showed you guys this. I probably should have hidden this deep somewhere so you couldn't see it, but you know what the phrases are. But let's go ahead and remove all the vowels from our phrase. So remember, phrase is a string. A string is an array of character. An array you can iterate over with a list or with a loop. So I'm going to say for tab into I equals 0, I is phrase.length. So I want to go the length of the phrase. And simple as this. I want to say if phrase I does not equal a, and the reason I want to use and here, in our previous videos, we used or in our situation like this where we wanted to exclude some stuff. But here, I want to print everything that is not these. So if it is any one of these, it's going to fail and it's not going to print. So phrase I equals, or does not equal, sorry, E, and let's copy and paste this just to make it easier. So E-I-O-U. So E-I-O-U. So there's all the vowels. And, you know, you're probably sitting there yelling at me, oh, what about Y? You know, Y is important too. Yes, Y is important, but, you know, in a case of this, Y is one of those sometimes cases where you kind of need it for the sentence. Oftentimes it makes the sentence make absolutely no sense when you don't put the Y in there. So that's why I'm excluding it in this case. So what we're saying is we're saying for every single character in our phrase, if it is not any of these characters, well, we want to print it. And remember, we can use our console.write to print it all on the same line. So we're going to say console.write phrase I. Very straightforward. Now at the end here, I'm going to say console.write line because I don't want to have, you know, please continue, yada yada, or press any key to continue. I don't want to have that on the same line. So I'm going to run it. So as an English speaking person, you can sort of read this. The quick brown fox jumped over the lazy dog. Now, you know that because I have the sentence right here, but if somebody was to text you this, you know, kids nowadays, they send texts that make absolutely no sense. This is kind of one of those texts. You can decipher what the meaning of the saying is. So let's try another one. So this one is a little bit more, you know, loose, I'm going to say. But even though the words in this phrase are completely disorganized, you are still able to read what the sentence is trying to say. Now, I obviously know what this is. Towards the end here, it gets really confusing. But if somebody texted this to you, boom, you know exactly what they're trying to say. Now, let's try this. So I'm going to print that console write line, and then I'm going to immediately print our phrase afterwards. Look how many letters we cut out. And I need to actually make our console window bigger. So, you know, we probably cut a fourth of the entire phrase out, and it's still relatively readable. Let's go back to our original right here, run it. Again, about a fourth, maybe a fifth, you know, something around there. But this one is pretty easy to read in itself. It's like you text somebody, you know, you're texting a friend in like shorthand or short script or something like that. And finally, let's try our last phrase just to see what happens. Now, this one, if anyone doesn't remember this from, you know, elementary school or whatever, my very educated mother just served us 9 pizza pies is the saying that I learned, at least back in the day, to remember the planets. You got Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, and then pies, I guess. Just add it to the end. I don't know why they put it in there. It's there though. But this was a phrase I learned to learn the planets. And you can see here, you know, again, this one isn't as clear as the quick brown fox jumped over the lazy dog, but it works. So my very educated mother, it kind of looks like dedicated, doesn't it? My very dedicated mother just served us 9 pizza pies. So again, not as clear as the other one, but you can still get the point. Somebody can decipher this meaning. And also, just for, you know, fun fact of the day, if anyone was wondering why I chose this sentence uses every character of the alphabet. You know, when you go to Word and you go to select like a font, that font is stored on your computer as this sentence. So they'll store this sentence in all lowercase. They'll store this sentence in all capital case. It's actually kind of a really neat way they do it. It allows them to distribute their font types to your computer in a way that's kind of readable and understandable and something like that. But this has A through Z in this one sentence, which is kind of neat. So anyways, there's that. Let's kind of ramp things up a bit. We can get a lot more complicated here. Another thing you may have seen in your English class is your teacher says, read this pamphlet or whatever, and the pamphlet looks like gibberish, but you can still read it because the first and the last letters are all in the right spot. So I'm just going to again remind you, this algorithm is kind of intense. There's many different ways to do this. I just chose a way to do it, but this is an algorithm that is probably even beyond the first year of computer science at D20. This is a complicated, mind-bending algorithm. But let's see if you can stay along and see if you can understand exactly what's going on here. So the first thing I want to do is I want to take each word and consider it by itself. Jumped. I want to consider this by itself. I don't want to consider it as a part of an entire sentence. So the way I'm going to do that, if you remember from our string manipulation unit, I'm going to use the split command on phrase in order to get an array of strings that is, this is the first index of the array, this is the second index, this is the third index, so on and so forth. So I'm going to say string array split equals phrase.split. And I'm going to split based on a space. That's the only thing I care about. I specifically, designed these sentences so that there's no punctuation or anything like that, nothing that we have to worry about. And remember, so split is the name I give it. I'm declaring it as the type of a string array, and phrase.split will return a string array. It'll return this phrase split with this as the delimiter, so all the spaces. So this array is now the as the first index, quick as the second index, so on and so forth. So now, I want to go through every single character of my array and alter it. I want to basically print the first and the last character just like normal, but I want to jumble up the inside a little bit and get some randomness going on here. So I'm going to say for tab I split.length. Now I want to go through the split length.length, not the phrase.length, because the phrase.length I would be essentially each individual character. If I do the split, then I'm looking at each word itself. So in here, I'm considering each word by itself. And what I'm going to do is I'm going to say character first equals split I 0. Now, what I'm doing here is I'm storing the first character. That's what this denotes, the first character of the ith word. So the very first time we run our for loop, we have I is 0. So in this case, I'm taking the first word, so the, and I'm storing the first character of it. Similarly, I'm going to do the same thing with the last word. So it's a little bit different though. So I still want the first word, but I want the last character of the word. And the way I do this is by using the length. So similar to what we did right here, except this is the length of an array, a string array. I want to get the length of the string itself. So what I'm going to say is I'm going to say split I dot length, and I don't want the entire length because remember the entire length is always going to be 1 plus the maximum. So I want to subtract 1 on it. So now this is kind of like weird syntax, right? So I have split.length minus 1 inside this value. But if you remember, dot length is an integer. You can see right here that it returns an integer. So this is an integer. I'm subtracting 1 from it. So this entire, everything that's highlighted is indeed an integer. So I'm going to store that in here, and that's going to get the last element, the last letter of the given word that I'm looking at. So the next thing I'm going to want to do, because a string is, it's not near as manipulable as a character array in itself, I want to convert my string, specifically split I, into an actual character array. Again, I kept saying a string is a character array effectively. It's similar. It's not exactly the same. So we're going to say this. We're going to call this the new string. And we're going to say split I dot to char array. So if you remember, split I is the word we're looking at. So the split I, I'm going to turn it into a character array. This is going to equal the whole thing. Now, there's many ways to do this next part. This next part is the jumbling up the middle part. You know, we could create an array, store all the values in it, randomly pick one, and put it in the, put it first before the other ones. We could do something like that. But that, we have to create more variables to hold things and do stuff, and we're going to do it a little bit more simpler, but a little bit more exhaustive, expensive kind of way to do it. We're just going to go through many times. So let's go through 20 times. We're just going to go through and we're going to swap letters. Remember our bubble sort from our array unit? We're basically just going to swap middle elements around. So I created this random object up here, and I'm going to use that random object to select two random indices that are somewhere in between the first and the last. So I'm going to say first index equals rand.next 1. Now I'm starting at 1 here because I don't want to include 0. I don't want to swap the first index. The first index should stay as is. Now I'm going to go here. I'm going to say split I, because I'm looking at the given word, dot length -1. Now, if you remember, rand.next, the max value that I give it is exclusive, right? So it doesn't include that value. So in the case of this value is 3, so -1 is equal to 2. So this is saying between the index 1 and 2, or at least you would think. However, the 2 is exclusive. It doesn't consider the 2. So what this is going to equal for the word the is the first index over and over. So it's just going to swap with itself over and over again, specifically for a 3-letter word. So let's go ahead and copy this because we're going to need this again. And we're going to call this the second index. So for the as the example, it's not that interesting, but let's look at sentence. Sentence has all of these internal characters that we could just flip-flop around, move around, and do something with. If we look at disorganized, it's even more. We have a whole bunch of letters to swap around. So that's what we're going to do. So now what we want to do is we want to create our temporary variable because at this point we want to swap, right? So we're going to say temp equals, and then I want to store this as the first index of our string. So we're going to use new string in this case. First index. And I got to make that a capital I. Cool. So now in new string first index, I'm going to set it equal to new string second index. I'm going to perform the swap. And now I'm going to finalize it by saying new string second index equals temp. Now, the reason I decided to store it in a character array like this is simply because of the fact that this is not possible with a string. You can't set individual characters of a string without getting super complicated. This is just a nice and easy way to do it. So now that we have this, I'm going to save our character array back into our original word, so into split. So I'm going to say split I equals new string, new string. Now, you haven't seen me use new string before. I actually have to create a new object in order to convert this array of characters into a string again. But in the end, this new string is going to be exactly what I want it to be. It's going to be the kind of mutated, manipulated way we did things. So I'm going to increase this to 50 just to ensure we get a good jumbled up mess, for the bigger words like disorganized. And let's see what we get. So first off, I'm going to have to go through and I'm going to have to print the word. Now I know because I only print based on spaces, if I just add a space after every element in split, I'll print the correct thing, what I want. So for tab, split.length, and I'm going to come down here and I'm going to say console.write. Remember, write, not right line. I want it as English reading, not up and down. Split I plus that space I was talking about. And then at the end, we're going to console.writeLine. And let's run it and see what happens. So the quick brown fox jumped over the lazy dog. So we kind of got lucky on like lazy, it just happened to land the correct way. But brown, it's a little switched up. Quick is a little switched up. Jumped, but you can still read this, even though it looks like gibberish. You can still read this. You can still understand this. Let's go to one of our more complicated phrases. Oops. So even though the words in this phrase are completely disorganized, you are still able to read what the sentence is trying to say. It's weird how your brain can put things together. I mean, if you think about it, when your eye takes in information, technically, it swaps and your brain like flips it upside down. It's a cool study. I recommend you guys look into it. But your brain does some super cool things that honestly a computer can't do. A computer trying to figure this out would have a tough time. It would just basically have to look at the letters and see that, oh, there's this collection of letters that can make this word, something like that. Your brain sees it in a very different sort of way. So it's really neat to know that your brain is stronger than a computer in many ways. So let's try our last one. My very educated mother just served us 9 pizza pies. Pretty easy to read. And it's really cool how your brain can do this. But now this algorithm right here is kind of messy. It's kind of ugly, But it gets the job done. It does what we want it to do. You could put some more interesting phrases in here and get something really neat. You could send this to your friend, say, hey, can you read this? I wrote an algorithm that generated this. How cool is that? So I recommend you try something maybe not this complex, but try to create, now that you know kind of the basics of programming, try creating an algorithm that can do something interesting. Show it to your friends, show it to your family. Get some hype around it. Get them interested in what you're trying to do. But anyways, let's go to our last problem. So we're going to comment this out. And let's go to our last problem, which is calculating the value of pi. Now, if you look here, we're going to be using the Gregory Leibniz series. I probably butchered that completely. But we're going to be using this series to calculate the value of pi. The reason we're doing this is it's a pretty straightforward algorithmic method to calculating pi. So this right here, we're going to say pi equals 4 divided by 1 minus 4 divided by 3. So the way this pattern works is you go minus, plus, minus, plus, minus, plus, minus, plus, yada, 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 so on and so forth. You then start at 1, and then you go every other odd value. So 1, 3, 5, 7, 9, so on and so forth. So let's go ahead and use this series to calculate pi. So I'm going to come in here, and I'm going to say, well, first off, we need to create some new variables. So we want to know what pi is. So decimal pi, and I'm just going to default that to 0 for now. I'm going to create another decimal. And also, by the way, the reason I'm using decimal here is because remember in our variables video, a floating point number is only precise to a certain number of digits. A double is a little bit longer than that. A decimal is the most precise when it comes to going down many digits. So that's why I want to use a decimal in this case. So I'm going to create val. Val is the value that we're starting with. And if you remember the series, let me open it up again. We start at 1. So I'm just going to hard code 1 in there. I'm going to start us at 1. Specifically 4. I said that very poorly. We're going to start the value at 4 because that's what we start at. We're going to start at the first index here, which is the value 4. My apologies. So we're going to start at 4 here. And then what I'm going to do is I'm going to create a Boolean that's basically what I like to call a toggle Boolean. This Boolean is just going to go back and forth. And I'm going to call it is subtracting. And I'm going to initialize it to true because, again, if we look back at our series, the first thing we do is subtraction. So I want to start it at is subtracting. Now, the next thing I want to do, because I already used 1, I want to start at 3. I already used 4 over 1 in this case, that's why I got the value 4, and I want to start at 3. So I'm going to create a long, and I'll explain why I'm using a long here in a minute, but I'm going to call it alternating odds, and I'm going to initialize it to 3. Now, the reason I'm using a long here is because if I used an integer or a short, if I used an integer after 2.1 billion elements, which this algorithm is going to run through pretty quickly, it's actually going to loop back around and start doing negative numbers. So instead of being 4 over 2.1 billion or whatever, it's going to be 4 over negative 2.1 billion, which is going to make our results very opposite what they should be. So we're going to use a long so that we can go into the very, very, very long digits or very long numbers without having any overflow issues. So now that I have this, I'm going to do something that I like to call terrible programming, and I mentioned this in the loops video. This is bad programming. While true is never a good thing, this is quite literally going to run forever. If I didn't put anything in here to break out of it, then I'm literally going to run in this little bit of code forever. My program would effectively halt. But we're going to put that in there in this case just because it does exactly what we need it to do. It's going to continuously calculate pi to a more precise value. So very simple in here. If is subtracting equals true, then I want to do something. Otherwise, I want to do something else. And remember, I only have to use an else here because the only other possibility for is subtracting is false. So it's the same thing either way. So I'm going to say val. I want to use my val right here because remember, this is the value that we're kind of storing it up in. Val minus equals for m. The m is what I use to typecast it down to a decimal because I want to keep that precision. For m divided by alternating odds. Pretty straightforward, to the point. For the other one, I just want to change this to a positive because remember, we just go negative, positive, negative, positive, negative, positive, or adding, subtracting, so on and so forth. So now, remember how I said is subtracting is a toggleable Boolean? It switches back and forth every time we run this algorithm. That's what we're going to do. So I'm going to say is subtracting equals not is subtracting. Now, what you would be thinking of, a more clear way to do this is I know is subtracting is true here, so I'm going to say is subtracting equals false here, and is subtracting equals true here. This would do exactly what I wanted to do. However, this is 2 lines of code as opposed to the way I did it, which is 1 line of code. So I'm saying set is subtracting equal to what is subtracting is not. So if is subtracting is true, I'm going to set is subtracting to false. If is subtracting is false, I'm going to set it to true because the exclamation point here says do the opposite. So that's what this is for. Similarly, our alternating odds needs to go up. So remember, I'm using 3 at the very beginning. I need to go to 5 next, and then 7, and so on from there. So I'm going to say alternating odds plus equals 2, because I want to add 2 to it. I don't want to just add 1 to it. I want to add 2 to it. I'm going to say pi equals the new value, and I'm going to say console.writeLine pi. And that's as simple as it is. This algorithm is just going to run forever, continuously adding on to value and printing pi. So if we run this, we can see that, first off, it diverges to the first few decimal points very, 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 very quickly. We can see right here that we already have 3.1415, and it's kind of approaching 9. It's bouncing between 8 and 9. I don't know if you're going to be able to see that in the video very clearly, but it's starting to approach 9. But at this point, it has to go through so many iterations. Now, I'm going to show you kind of another cool little trick. So because this runs forever, I'm going to press F5, and now our debugger is attached to the process. So you can see here, I'm calculating pi. We're attached to the debugger. Visual Studio is tracking this, and we can see, we're using a good percentage of our processor. It's maxing out at a core sometimes, but not often all the time. And our memory is pretty static at 10 megabytes right now. So what I can do with the debugger is I can pause it to see exactly where we're at. So check this out. I want to see what alternating odds is right now. So I'm just going to put a breakpoint right here. Now, again, you don't need to know this. This is just additional fun facts. Alternating odds right now is at 1.2 million. If you remember our series here, over 1, over 3, over 5, over 7, we've already gone up to the point where we're at 1.26 million elements. So we're getting very, very, very far out there. So let's go ahead and another little fun fact. This algorithm right here, this is the most expensive operation. Literally printing to the console is the most expensive thing. So what we're going to do, we're going to remove that breakpoint, and I'm just going to comment this out. We're just going to let our algorithm run for a bit by pressing F5. So we're just going to let this run for a bit, and now you see how it's just capped out using 100% of my processor. That console write line was putting a whole bunch of delay in the system that it couldn't use the entire thing. Now this algorithm is using my entire processor, it's maxing out, it's calculating much, much faster. So in this time that I've been talking here, it's been going through calculating more precise digits of pi. So like I did last time, I'm going to put a breakpoint. It's going to stop our code, so our code is no longer running, it's paused. We're going to check this out. Alternating odds is already at some massive huge number. We weren't running for very long, but you can see how absolutely massive this is. Now, similarly, if we look at pi, we can see pi is 3.14159.264. So this is where it gets a little bit off. This is where pi is not correct. The value of pi is actually 3.14159.2654. So that's at least what I remember it up till. So we're getting pretty close. So let's go ahead and remove this breakpoint. I'm going to continue the code, and we're going to let it run for, another, let's say 10 seconds. This algorithm it's what we call a diverging algorithm, or a converging, algorithm. It converges on an answer. However, because pi is infinitely complex, every single computer on the planet working together could not solve this problem in any period of time, an infinite period of time. It literally couldn't solve it because pi literally goes on forever. So after that quick banter, we've gone a little more. Let's see what happens. So I'm going to mouse over alternating odds. It's massive. It's a huge number. I don't even want to try to look at that. But let's look at pi. 3.15159.265, and then again. So we're right here. So we just went a huge step from where we checked the first time, and we only got one more digit of precision. That's how expensive some of these computer algorithms are to solve. But you can see here, through the use of pretty simple logic, really, we can do something cool. We can calculate pi to, some level of digits. Again, I could leave my computer on here for a few days, and eventually, it would get to, a few more decimal places, like actual precise. But we're not going to wait for that. We're just going to assume that, yes, this algorithm works. We will eventually calculate more digits of pi. So anyways, ladies and gentlemen, that's going to be the end of our last unit. Now the only thing up to you is to go take that final assessment and breeze through it, which if you've watched every video, I think you'll do perfectly fine at it. It's pretty straightforward. It's nothing, near as complex as this. And I really look forward to having you guys in class next semester because we're going to have a lot of fun. Learning how to program with a bunch of like-minded people is a ton of fun. It's a cool skill to have, whether you want to go into computer science or software engineering or not. It's just a good thing to know. It's a good thing to understand. It's where the world is going. It's better to know what your computer is doing than not. So I look forward to seeing you guys in class, and thank you for watching these videos.